So this is the second part of C4, moving on to group 1 metals and group 7 halogens. So the group 1 elements are all what we call the alkali metals, and that's because they all react quite vigorously with water and they form alkaline solutions. So the elements we're focusing on in group 1 are lithium, sodium, potassium, rubidium and cesium. Now, francium we tend to ignore because it's radioactive, and so we can't really. The properties of that would be different. Rubidium and cesium we can't use in school because they're too dangerous, they're too explosive, and so most of our questions will focus on these three. But then if they're going to ask you about rubidium and cesium, what they'll be asking you is, can you predict what their properties would be like based on the top three? So because they're also reactive, when we store them under oil, and this is because they'll react with the air. And you can see, particularly if you look at the potassium, some of this has already reacted with the air, and it's slightly tarnished on the surface. So they aren't like normal metals in the sense that they appear shiny. They are if you cut them, because they're all very soft, which again is another unusual property. You can tell from this that lithium is less dense than oil because it's floating, but sodium and potassium are both more dense than oil because they're both sunk. They're all less dense than water, however, and they're going to float on water in each case. So the reaction that takes place is that we get the metal, which could be lithium, sodium or potassium, reacting with water. We get the metal hydroxide, which again could be lithium, sodium or potassium, or rubidium or cesium, and it forms metal hydroxide and hydrogen gas. So as an example, we'd get sodium plus water goes to sodium hydroxide and hydrogen. You need to remember that hydrogen, the test for hydrogen is that it burns with a squeaky pop. So that's the test for hydrogen. So they might say to you, they might give you the reaction and say that lithium reacts with water and that it forms a lithium hydroxide and a gas that burns with a squeaky pop, and then you've got to identify the gas. So in symbols, this would be an example. We've got sodium plus water, H2O, goes to sodium hydroxide and hydrogen. Remember, hydrogen is a covalent molecule, so it's diatomic, it's got two atoms in it, because it's got a shared pair of electrons. And to balance it, you put a 2 in front of everything apart from the hydrogen. If I just do potassium as another example, so it would be, I'd need 2 potassium atoms to react with 2 water molecules, and exactly the same, I would form potassium hydroxide. Remember, hydroxide is OH. The hydroxide ion is a polyatomic ion, it's OH minus, and obviously the sodium in this case would be Na plus, and it's the same here. It would be K, potassium is a plus and OH is a minus, and also, and then we're left with hydrogen gas, which is H2. So they all float on water and they all fizz, and that's because they're producing the hydrogen gas, and that will push them around the surface. Now their reactivity increases as you go down the group. So cesium is properly explosive, which is why we can't use it in school. Lithium will fizz vigorously but doesn't get hot enough to melt. Sodium will then melt, it will form like a solid ball, and then potassium will then get hot enough to ignite, and it will burn with a lilac flame. You can also see that their melting point, so this is a graph along the bottom, I know it's been cut off, but it is melting point along the bottom in degrees C, and you can see the melting point decreases as you go down the group, which you might be asked to predict. So you might have a question where you're given these values in a table, and then you're asked to predict what the melting point of cesium would be, and obviously it's going to be less. So this is lithium in water. You can see it fizzing, you can see the hydrogen gas being produced, but you can see it's not changed its shape because it's not melted. You can see sodium in this case, and you can see it's formed a ball, and that's because it has melted, and the ball provides the lowest surface tension. You can see in this time the water's had universal indicator added to it, and it's turned purple, and this is an indicator that we've got an alkali solution, the alkali being sodium hydroxide. So remember, any hydroxide is an alkali. And then you've got potassium, and now you can see that it's burning with the lilac flame, slightly more explosive, slightly more vigorous. And so this is the most violent reaction because it's the most reactive. Now the reason this is the most violent reaction is because what each of these elements do, which we talked about in the last video, is when they bond, is they've got 2 electrons in their inner shell, for example for lithium, and then they've got 1 electron in their outer shell, and this is the electron that they're going to lose. Now, what happens if you imagine comparing lithium to potassium, for example, which has got 2 electrons in its inner shell. It's going to have then 8 in its outer shell. Sorry, not in its outer shell, its second shell. Another 8 in the third shell, and then its fourth shell. Then it's just going to have its 1 electron. So because this is much further away from the nucleus, there's a much less attraction. So the key idea, it's much easier to lose an electron on a bigger atom than it is on a smaller one. So potassium reacts more violently because it's easier to lose that electron there from the outer shell. And lithium would form a +1 ion, just the same as potassium would form +1. Now, another key feature of all the metals is that when we put them in and heat them up, metals burn with specific colours. And that's because the metal ions will vaporise. Now, what happens when they vaporise is they absorb heat energy, and that causes the electrons to jump into higher shells. And when they drop back down, they release light energy. Now, the different metals release different colours of light, so we call this flame testing, and the question might be, describe how you would carry out flame testing. So, first of all, what you do is you take a moist loop of wire, and you would dip it into a solution of hydrochloric acid. Okay. What you then do is you place it in a metal sample that you're going to test. And so you put your loop into the metal sample so that you end up with some of the sample on the end of your loop, and then you put it into your blue Bunsen flame, and that will reveal the colour that it burns with. And you must wear goggles when you do this as a safety point. So for example, lithium, if you can see, here's the wire loop. It's already been dipped in the acid and had the sample put in, and it burns with a bright red flame. So remember, lithium produces a red flame. This is sodium, which produces an orange flame, and then lilac for potassium. Okay, please put lilac, don't put purple. So the last one is lilac. So just to summarise, if you're asked to write an equation to show the formation of ions in the group 1 metals, so for example for sodium, we start off with sodium, the element, and what happens when it reacts, and this is the same for all of them, is that they form +1 ions, so it will become sodium +1 +1 electron, so it loses that electron, and we've said that it's easier to do that as you go down the group, and so they become more reactive. So the next group of elements we're going to talk about are the halogens, which is group 7, and for these we're going to focus on chlorine, bromine and iodine. Now chlorine, the word chloro means green, so chlorine is a green gas. You see this word in chlorophyll or chloroplasts, anything that's green we tend to use the word chloro. Now the use of chlorine is it's used to sterilise tap water and swimming pool water, and this is because it kills harmful bacteria and hence makes it safe to drink or to swim in. We also use it to make pesticides, plastics, such as PVC, which is polyvinyl chloride, which is an important commercially available plastic. The next one down the group is bromine. Now you can see we've gone from a gas in this case to, you can see just at the bottom, a liquid. But because its boiling point is approximately room temperature, it turns into a vapour very easily. So bromine is an orange liquid. Okay, it's used to purify water and to make flame-proofing agents. We also use it in pesticides, medicines and dyes. And it's one of only 2 liquids on the periodic table. The only other liquid on the periodic table is mercury, which is liquid metal. Iodine is the last one we'll talk about, which is a grey solid. Okay, but iodine has a unique feature, which is that when you warm it very, very gently, it will produce a purple vapour. And what's happened here is it's gone straight from being a solid straight to being a gas. It's missed out being a liquid altogether. Now, going from a solid to a liquid, you would know is melting. Going from a liquid to a gas, you would know is evaporation. The name for the process of going straight from a solid to a gas is called sublimation. So that's a unique feature that iodine can do, and there's not many other materials that will do sublimation. Dry ice, carbon dioxide is one. If you go back the other way, you go from a gas to a solid, you don't need to remember this one so much, but it's called deposition. And the use of iodine is it's used in antiseptics to sterilise wounds. So the reactions of them, they will react quite vigorously with metals. So this picture shows a reaction of potassium and chlorine gas, and you can see it's producing this bright yellow chloride, this potassium chloride. So the reaction would be any metal plus any halogen, just their name as elements. This is. And what all we do is we change the ending of the halogen to "ide". So for example, if we reacted sodium and chlorine, I'd get sodium chloride. And if I put that into symbols, I just put the symbols for the elements, remembering that if I've got a gas, it's 2, and then it's NaCl, because that's a +1 ion and that's a -1 ion, and I balance it at the end. Another example would be aluminium plus bromine, which would give you aluminium bromide. So another key feature of the halogens is that it can undergo displacement reactions, and a displacement reaction is when a more reactive element swaps with a less reactive element. So as an example, chlorine is at the top of group 7. Fluorine is above it, but we tend to ignore fluorine because it's the most reactive element, so we tend to ignore it because it's slightly different. Bromine comes next, and then iodine. At the bottom there's astatine, but again that's radioactive, so we just ignore that. But their reactivity is the opposite of group 1, so it increases going up the group. And the reason for this is again the opposite reason for group 1, because what happens is the atoms get smaller as we go up, and because unlike group 1 metals that lose electrons, the group 7 elements gain electrons. And so it's easier to gain an electron if you're a smaller ion. So chlorine is the most reactive. So chlorine will displace bromine. So if I react chlorine and sodium bromide, for example, the chlorine will react. If I reacted bromine and sodium chloride, it wouldn't react, because when the chlorine has reacted with something else, so the sodium, it's formed a bond, and that will be more stable than if bromine is there. So because it's the most reactive, if I'm reacting the element with a less reactive compound, the element will displace, so it will kick the bromine out, and so I'll be left with sodium chloride plus bromine. So again, you can see it's gone from ide to ene and ene to ide, because we change the name when it's in a compound. And the sodium stays where it is. So in symbols, this would be Cl2 plus 2NaBr goes to 2NaCl plus Br2. So I could also do this chlorine reacting with sodium iodide, and it would be so chlorine plus sodium iodide would give me sodium chloride and iodine. And bromine is more reactive than iodine, so I could do bromine plus sodium iodide would go to sodium bromide and iodine again. But again, iodine won't displace bromine or chlorine because it is least reactive. And that's just the general symbol equation that you could use for this. So then we move on to the topic of metals, which we're going to start in this video. So you should know the properties of metals. They're fairly straightforward. They conduct electricity, they conduct heat, they're strong, they're tough, they're shiny, they're malleable, which means you can bash them into shape, they're sonorous, which means when you bash them they make a ringing sound. They're ductile, which means that you can pull them and draw them out into a thin wire. They've got high melting points and boiling points. They've got high densities. Some are magnetic, that's iron, cobalt and nickel are the only ones that are magnetic. And then you can make alloys when you mix them together. Properties of non-metals are basically the opposite, so they're typically poor conductors of electricity, poor conductors of heat. They're not strong or hard, they're dull. They're brittle, which means they break apart. They've got low melting points and boiling points, low densities, and they're not magnetic. And transition metals is the group of elements in the centre of the periodic table. Now, their general features are they're less reactive than group 1 and group 2 metals, which obviously lose electrons much more easily. They're often used as catalysts to speed up the rate of a reaction. So the ones that you need to be aware of are iron, which is used as a catalyst in the Haber process, nickel, which is used as a catalyst in the manufacture of margarine, and platinum, which is used as a catalyst in catalytic converters, and that saves time, energy and money. So those are some examples.